you go. Okay, now we are streaming. We good. All right, so now we click save, and if I go back to the command line, oops, not this one. This one, it should be here. And let's see, is it actually here? It is. There we go. It's over here. So now I can repeat the previous command. I can use the up arrow key to locate a command that I have run earlier. And now we can specify test driver.circ n-tty table, and then press the enter key. It complains that reference.circ is missing, and that's because they're not in the same folder, but that's okay. You just click OK, and then you have to help Logisim to find it. Oh, you cannot see the dialog box because it pops up in my other window. Let me move that to where you can see it. There we go. So you can just click OK, and then navigate to where you saved the reference.circ. So in my case, it is under the CISP310 folder. And here we have reference.circ. And it just says select, and the program ran. So is that okay? All right. So the tricky part, because some of you are using Windows and some of you are using, oh, you guys could not see where I found it because it's on a different screen. But anyway, it's just it's just that you have to find the file for Logisim, and it has to be able to locate it. Let me do that one more time, but this time I am going to move all the dialog boxes to where you can see it. This is the first one. We have seen this before. Click OK. And this is the one that you did not see because I did not move it into the view of the projector. So over here, you just go to the folder where reference.circ is located, and it ran like that. All right. So the tricky part is how you specify the path to the jar file and also to the circuit files, because that part is dependent on what operating system you're using. So the instruction contains instruction specific to Windows, which is using %homdir or something like that to refer to the home directory. And then with Linux, you use the tilde symbol to refer to the home directory. But the bottom line is you still need to know where you put all the files to get this to work. And some of you may be saying, but this is more command line stuff than I have ever done up to this point of college. You can expect more in your future. So this is just a good warm up, for things to come in a 4-year university. All right, are we good so far? Did I answer the question? Okay, excellent. All right, so now that we can continue, we are moving on to, well, actually, we are not ready to move on yet, because there's one last section that we haven't really talked about yet. So we'll go ahead and revisit this particular module. And what we have not talked about yet is why is NAND useful? All right, to explain this part, the first thing we need to do is to remind ourselves what is NAND, N-A-N-D. Can someone remind me what NAND represents? Why is it spelled N-A-N-D? Yes, go ahead. Not and, right? Okay, so very good. So it's the negation of an and. So the way we can, okay, I'm just switching back and forth to my, to my command prompt, because I'm using that to basically write my own notes too. So copy, nope, it's just nvim today's date. There we go. All right. So x NAND y is basically the same thing as the negation of x and y. There we go. So I already presented what NAND is representing last time, and this is just a quick review of what we knew from last time. So now you guys may say, But that is not an operator that we learned in CISP360. In 360, we learned about negation, we learned about conjunction, which is and then we also learned about disjunction, which is or. But nobody taught me anything about NAND. But that's okay, because as you can see, NAND can be expressed using logical operators that you are already familiar with. So the next question is, well, fine, but how useful is NAND? I mean, it doesn't seem like a useful operator at all, because otherwise I would have learned it in an earlier class. Well, as it turns out, your previous class, CISP360, taught you negation, not conjunction, and disjunction, or, because those are the things that we use a lot, in our conversation. When was the last time somebody used NAND in a normal conversation? Never, right? We simply don't use that operator. But in computer science, NAND and NOR, okay, which is the counterpart of NAND, they are both really useful. So the first thing we want to do is now to say, if I just want to express not x, how can I use NAND to express not x? So that's one question, because I want to find out, can I use just NAND and a whole bunch of NANDs to express the operators that we are already familiar with? And we'll start with negation. Go ahead.
X NAND X?
X.
Sorry, X NAND X?
Yep. So this is the same thing. I claim that this is the same thing as X NAND X. All right? And if you had reviewed or previewed the notes ahead of time, this is nothing interesting at all, because you would have read it in the module and go like, yeah, Taki, you're just repeating what you wrote already, which would be ideal, okay? Because I really want you guys to have the time to read the module ahead of time. Just a little bit, okay? If you don't fully understand something, not a problem. Write down your question, so when I get to that topic, you can try to make sure that I address all of your questions. But it is important for most people to read ahead of time, so that these concepts are not foreign by the time I talk about it in the class. For a very small minority of people, you probably don't need to read it ahead of time, but that would be the minority, small number of people. All right, so what am I going to do with this? Do you think I'm just going to say, do you think I expect you to just think, well, if Ted says so, it's fine. We'll just accept it as not x is x NAND x. Nope, that is not the way I want to teach. So what do you think I want you guys to do when I present you a statement without any proof? Test it, verify it, validate it, right? You show us why that is the case, okay? So let's go ahead and do the next step, which is really just to expand what NAND is about and turn it into operators that you already know. All right, but that still looks kind of like, I'm not so sure, okay? So one way you can test this is to use a truth table. So in this case, a truth table like this would involve x, which is the only independent variable, one of the expressions, which is not x, or just the logical not of x, and then the other one is what we thought is the same as just not x. And x as a Boolean variable can take on the values of false, true. So when x is false, not x is true. And what about over here? If x is false, false and false is false, not false is once again true. And then on the next row, we look at what happens when x is true. Not true is false, okay, that's an easy one. And then true and true is true, not true is false. So using a truth table, I have just shown that the expression not x is equivalent to the expression of not in parentheses x and x. Are we okay so far? And this is a very useful technique when you're dealing with Boolean expressions. If you want to see if two Boolean expressions are equivalent to each other, one way to do it, not the only way, but one way, is to use a truth table. And when you use a truth table like this, you don't even need to bother with Boolean algebra. You don't have to say, oh, okay, we know the identity rule because x and x is really just x itself, and therefore we derive the equivalency between the two expressions. No, you just brute force it. Okay, you evaluate every single case for each expression. If they are the same for every condition you give to the expressions, then the two expressions are the same. So now we move on to the next one, which is x and y. Okay, so we want to look at x and y, and we ask, can we use a bunch of nands to express the same thing as x and y? So it would appear that this should be easy, right? Because this is the same thing as the negation of x and y, because after all, NAND is the negated AND. So if we negate it again, then we end up with the original AND. But that's not acceptable because I said I only want to use NAND on the right-hand side. This one has a negation on it. So how do we solve that problem? How do we get rid of the exclamation point and somehow only use NAND in the expression? I have shown you how to do it already, because earlier I showed you if I ever need to say not something, I can just say that something NANDing with itself. So that means in this case I can say x NAND y NAND itself, which is x NAND y. All right. Are we doing okay so far? Are there any questions about how I derived x and y and only using NAND in the equivalent expression? So once again, we get into the issue of text said so, but is it actually the case? So what do we do? Truth table. Okay, so we're going to use truth table again. I mean, yes, it is a brute force approach. It's not very elegant because if you use Boolean algebra to derive the equation, it'll be cleaner and more elegant. But the truth table is just as good if you just want to verify. So in this case, we have a outer NAND, and then we have two inner NANDs. Okay. So I have just put in the structure of the operators first, and this is actually typically how I write expressions as well as program code, is to put in the structure and then go back in and fill in the components for the structure. So in this case, we have x NAND y, oops, on one side, oops, I got the spacing wrong, and then we have x NAND y on the other side. So that is the expression that we are trying to evaluate. We have two independent variables. One is x, one is y. They're both Booleans. So how many rows should I anticipate in this particular truth table? 4. Yep, that's correct. So we have 0, 0, 0, 1, 1, 0, and 1, 1. Those are the only 4 ways you can arrange values for x and y. We have exhaustively listed every single way to assign values to x and y in this case. So now, I forgot one column because I forgot the column where it is just the simple version of the expression. So this one is easy, right? Because it's all zeros except for the last row. And now we kind of have to go through all the trouble to evaluate the long, complicated one. So the way you do this is you really just do substitution. X is false, y is false, false and false is false, not false is true. Same thing over here. So now we end up with true and true, which is true, but the whole thing is negated by the outermost negation. So we have not true, which is false. Okay. And then we move on to the next row, do exactly the same thing, but this time y is true, x is still false. So now we have false and true, which is false. Not false is true for the entire thing here. And the same thing over here. So now we have true and true, which is true. But then we have the outermost negation. So we now have not true, which is once again false. The third row is symmetric to the second row. And because conjunction is commutative, we can just kind of go like, yeah, I think it's going to be the same as the second row, done. And then the last row has both x and y being 1 or true. So now we have to kind of evaluate that one. X is true, y is true, true and true is true, but not true is false. And the same thing on the other side. So now we have false and false, which is false. And then we have not false because of the outermost negation, which is true. So the last row is true. And now we have established the equivalency between x and y and the long gibberish that we just talked about. Because for every single possible way to arrange values for x and y, the two expressions give me exactly the same result. Are we good so far? All right, so we have one more to go. That one is not as intuitive because we have x, y, and this time we have x or y, the disjunction. So now we want to look at this and go like, oh man, that's going to be a little bit harder. If you know De Morgan's law, it's not hard because De Morgan's law is one of those really useful transformation, but it only works in Boolean algebra because it only works on an expression that has a negation of an and or the negation of an or. I can talk about that a little bit more, but right now I'm just going to give you the answer. Yep.
I think it's like not NAND X and then not NAND Y.
Okay,
And
I can.
then not NANDing both of them. Not sure.
Okay, so it has the same structure as the other one, which means we have a overall NAND of the entire thing, and then it has x NAND x on one side, oops, and it has y NAND y on the other side. So this is y NAND y. So I claim that this is going to do the trick, and the other way to say this using just NAND is x NAND x NAND y NAND y. Is that kind of what you were talking about?
Yeah.
Yep. Okay. It's hard to verbalize something that is structured, especially when we use the infix notation, because when you use infix notation where the operator is between the two values it's supposed to operate on, you have to rely on parentheses to indicate what do we do first. As it turns out, there is one notation where you don't need, there's no parentheses. It's called postfix notation, where you specify the values first, and then you specify what you want to do with the values. So in postfix notation, there are no parentheses because of the ordering of things. But we'll introduce postfix notation in a later part of the class, just not now. All right. So I claim that x or y is really the same thing as x NAND x NAND y NAND y. So now we're going to go through the whole thing again and use a truth table to either prove that TAC is right or for whatever reason TAC is wrong. So we will go ahead and specify the 4 cases again. And the third column is easy because I'm hoping that we all know what OR does because of CISP360 as well as CISP300 because that's a really fundamental concept that should be introduced 2 semesters ago. There we go. All right, so now for the complicated one, x is false, false and false is false, not false is true. Y is false, false and false is false, not false is true. So now we have true and true, which is true, but then we also have the outermost negation that turns the true into a false. On the second row, x is false, y is true. So now we have false and false, which is false, not false is true. And then y is true, so we have true and true, not true is false. And we end up with true and false for the outer conjunction. True and false is false, not false because of the outermost negation is true. So we get a 1 here. The next one is symmetric, so we can say a 1 also over here, And then for the last one, we know it's going to be 1 because we have x and x is 1, not 1 is 0. Y and y is 1, not 1 is 0. We have 0 and 0, which is 0. But then we have an overall negation, so not 0 is 1. There we go. All right, so as I drink water so I don't, my throat is not dry, you guys can kind of look at this and see if you have any questions. So are there any questions about, excuse me, the truth tables? Yep, go ahead.
So you did X for the one before the last one. I did X and Y, but why didn't you do not X and Y for the third column?
For the third column. Are we talking about this portion or this portion?
No, the one above it.
This one?
Yes.
And which row of the truth table are we referring to?
The third column, the X
The
and
third column.
why?
This one?
Yeah. Why didn't you do not X and Y? Because you said not X.
Oh, we want to express. This is what we want to express.
Okay.
Using NAND. So we want to make sure that what we want to express and the way we use NAND to express it are equivalent. Okay. Any other question?
I think on my head, wait, no. Yeah, it's just a simplified version of that. No, because like the way I simplified it was like not, and then parentheses, not x and not y. So it's like.
Right, but we cannot have not because we have to express everything as NAND.
Yeah, it's just basically a simplified version of that one. I just reversed it, I think.
Yep. Yep, because you were probably using De Morgan's law. No, okay, because that's exactly what De Morgan's law would have arrived at. Yep. Now, for those of you who want to know, how to derive this using just Boolean algebra, this is how we do it. So x or y is the same thing as not x or y, which is the same thing as not of x or y. So the negation of x or y once we apply De Morgan's law, the inner negation becomes not x and not y. That's what you have.
Yeah, that is
Yep.
what I derived at the end.
But since we cannot use negation, we're supposed to use just NAND. So that means now we have the negation of x NAND x, because that's the negation of x, and y NAND y. And then we can do one more simplification because of this negation on this and. So now we arrive at the final form, which only makes use of NAND to express what we usually call OR. Yep.
Yeah, no, I went from the big one to the NAND statements, and then I went from the NAND statements to that statement over there.
Yeah, that works too. There are multiple paths to get to the same conclusion. So this is a lot of pine needles, okay? Because we're getting into truth table, we're trying to evaluate each row and find out to see whether the expressions are the same or not. But when we take a step back, what is significant about all of this stuff here? What is significant about, hey, we can boil logical negation, conjunction, and disjunction down to just NAND? What is the significance of just being able to convert everything to NAND? Now yep, go ahead.
Like you said earlier yesterday that you could just put all the operations as like NAND, and you could just rewrite everything in that way.
Right, but what is special about NAND? Until today, we look at NAND as like, no, that is a really awkward operator. But there's one thing from Tuesday that sets the NAND apart from the other operators? It has to do with, yeah, go ahead.
You can make any other operator from NAND.
Yep,
So-
but why is that important? I can make any other operator into NAND. Go ahead.
It's because like you can design a circuit and you can do anything with it, like any kind of operation.
Okay,
One design.
Close. Go ahead.
Is it because the NAND kind of logic circuit is a simple one compared to how, like, so we know how to make it, I guess?
Right. So I think both of you are trying to say the same thing. Okay, go ahead. One more.
You can just make a big thing of NAND circuits, and
Right.
then you can like just use those
Mm-hmm.
to write what you need
Right.
in terms of and all the other stuff. Because otherwise it'd just be like a what's the word again for just not a multi-purpose computer? It'd just be a single-purpose computer,
Special purpose, I suppose.
I guess.
Mhm.
You don't write programs for that one. It's designed into circuits to do that.
Okay.
But since a regular computer can do a bunch of other stuff,
Mm-hmm.
you can just use a bunch of NANDs
Yep.
and make what you need to do.
Okay, so you guys are all getting to almost the point that the point that I'm trying to make, which is a NAND gate can be made by using two P transistors and two N transistors. So now we have a connection from devices that we can just buy, no longer from Fry's because Fry's is no more, but you can go to a lot of online places to buy transistors. They're dirt cheap and you can just build your little test circuit. But the point is, even though the NAND gate only needs 4 transistors, and these will require more, it is still just hierarchies, right? Structures of NAND, which also means, yes, we can use transistors to do negation. We can use transistors to do regular and we can also use transistors to do regular OR. That is the significance of this entire discussion. If you take a step back and look at the pine tree, that is what the pine tree looks like, okay? We can implement all the logical operators that you are familiar with using just transistors. Are we good so far? All right. See, if I were a student in this class, the first time at least, I would probably be, like totally go like, wow, that is cool because now, I can connect what I have learned in the previous classes about logical operators to, oh, we can do all of this stuff using transistors. Okay, occasionally a lot of transistors, but nonetheless, it can be done in hardware. I can now connect logical concepts in programming to actual devices that I can buy and hook up wires and make it work. And I think that is significant because it really takes the mystery out of computers to a certain extent. So that's kind of one purpose of this class is to completely take the mystery out of computers. It's like, how does it do this? How does it do that? How does C work? Okay, how do I use arguments? How do I return a value? How do I use a pointer? How do I use a structure? What are local variables? How do they compare to the global variables? We will get to that point by the end of this semester. But we are still kind of stuck with transistors for the time being. Cool. All right. I think it is cool, but people can definitely disagree. So we are now moving on to section 4, which is going to help us transition to what today's real topic is about. Numbers and values. What is a number and what is a value? Aren't those two things really the same thing? So I'm gonna hold my hand up and you think about the quantity. Don't say what it is, just think about it. Okay? This is the quantity, which is a value. But by the time you say 5, it becomes a number. Because you can also say this is not 5, but heck, I disagree. This is 1 in base 4. That is correct. Or you can say this is 101 in base 2. You're correct as well. Or you can say this is 12 in base 3. You would also be correct in that case. So a number is a representation so that we can communicate a quantity with somebody else. It is a language, okay? It's an element of language when we need to let the other person know what quantity we are talking about. that is a number. But what a number is representing is a value. A value by itself has no inherent symbolic representation. It's just a quantity. Is that okay? Does everybody kind of get an idea of the differences? Yep.
So it's like a quantity or a value is like the universal like value for this thing. So 5 will be 5 regardless of wherever you are. But the
Or
way
how
you
you-
express 5
Yep.
will be different.
If you want to express this, it depends on what base you're using. Okay? All right. So with that in mind, we are now ready to transition to the next module, which is about base conversion. Now, some of you may have some experience with base conversion, depending on what classes you have taken, and also which college you took those classes from. So here we go. And does everybody have access to at least a mobile device at this point? Okay, because I'm going to take roll. I forgot to do that on Tuesday, so I'm going to do it today. And we're going to, so this is the typical way that I take roll. You don't have access to it yet, but I'm just going to describe how I usually get it done. So I would usually just use an activity in the form of a quiz. It's not actually a quiz. It is just a simple stupid question of what word TAC is using for roll taking purposes. So this is from last time. I have no idea why I used Zuze. So I'm going to change it to 5, okay? Because we just mentioned 5 is a word. So I'm going to say this is the word that you need to enter. Update question. You cannot see it yet. I have not yet released it. And I will give you a certain amount of time to participate in this activity to basically say, yes, I am in class, and as a result, I know what the answer is supposed to be. So I will give you, let's see, it is until the end of the lecture. How about that? That should be plenty of time. So until 10:20 a.m. today, you can go ahead and just enter that word, save and publish. Now you should have access to it. If you have already signed into Canvas, you can now refresh this class, and it should appear right after the companion assignment. And the name is reflective of today's date, which is 2022-08-0825, and it will say roll taking in it. So click on it, and the word for roll taking today is lowercase FIVE. If you're having issues with getting into that activity, let me know. You can do it on your phone too. If you have a Canvas on your phone, you can just do it on the phone. Because this is not massive typing. You're not trying to type an English paper on your phone, and I think it should be fine. That gives me a chance to drink some water and take a breather before we start to talk about the heavy duty stuff, which is base conversion. For those of you who are done, with the activity, you can also note the time because we are transitioning to a new topic in maybe a few minutes. So if you kind of jot down the time and say, okay, this is the beginning of the discussion of base conversion, that might help you locate which part of the video you want to review, just in case you want to watch it again. As the semester progresses, I will stop or basically decrease the amount of reminding of, oh, you might want to jot this down, you might want to write it down, you might want to do blah blah blah, because I am hoping that you guys will develop the habit on your own, as time goes on. All right. So are we ready to move on, or does anyone need more time for the activity? We all good? We all good? All right. Okay, so now we are moving on to the next module, which is right here, values, numbers, and bases. And as I said a little bit earlier, this is a heavy-duty module, and that's why you may need to take notes. Well, that's actually kind of a joke to begin with, because base conversion is easy. I said it was complicated just to get your attention, but you already know how to do it. You guys may say, some of you may say, yes, I learned this from CISP310 from a different campus. That might be the case. Some of you may say, but yeah, I learned about this because I was curious and I just kind of read material about it. But for the rest of you who has never been exposed to base conversion, let me present you with a different problem, and you tell me whether you can do that or not. So let me switch back to, no, not this one, but this one over here. So I am going to present you with a problem that you need to solve, and it is making change with a certain amount. So I need to pick an amount that is fun to work with. Okay, so maybe just that, okay? All right, so let's just say that you're working at McDonald's and you have to make change for $7.25 in the United States using the common coins and bills that we use. So let me first ask, how many people here feel comfortable and say, yeah, I can do that, not a problem, okay? And because for anyone who says, I really cannot do that, you might need to take some remedial math classes. It's not even math, right? Okay, so you guys would go like, but I want you to kind of be introspective and think about how you came to the solution, okay? Because my first solution to this problem is I'll just give the customer 725 pennies. That should do it. But that may not be a good solution, right? Or I can give the customer 7.25 divided by 0.05 nickels. That would also be a solution. Once again, may not be the best solution. So how did you come up with one $5 bill, two $1 bills, and one quarter? How did you figure that out? Yep.
It just comes to you naturally because you're not gonna want to carry 725 pennies or.
But where did you start? Did you start thinking about pennies and then nickels and then dimes and then finally go like, oh, okay, I don't need any of those. I need quarters. Yep, go ahead.
Start with the largest bill I can use.
Start with the largest, okay?
But take the largest
Same thing?
denomination.
Yep, largest denomination. All right. Okay, so you already know base conversion. If you know this, you know more than what you need to know to do base conversion. Now, let me mention why that is the case. So what we want to do is to look at the denomination in US currency. So we start with a penny, which is 0.01 of a dollar. And when you multiply that by 5, you get the next denomination, which is a nickel, which is 5 cents. And then if you multiply that by 2, you get a dime. And then you multiply that by 2.5 to get a quarter. And then you multiply that by 4 to get a dollar. Yep.
And sorry to ask this. Does the Boolean algebra relate to what we're talking to?
Base conversion to base 2, which is not Boolean algebra,
Oh, okay.
is way easier than this. Because at this point, I have not even seen a single repetition of the same multiplier, right? We got 5, and then a 2, and then a 2.5, and then a 4. They are all different. And then we can say, oh, okay, maybe it's a good thing that we get a $5 bill because it looks like we're repeating the pattern because the next one is a $10 bill, right? But then do we have a $25 bill? No, because we have a $20 bill. So it breaks the pattern again. Now we have a 2.5 to get to a $50 bill. There's no regularity whatsoever. And yet, you guys have mastered it. You don't even need a piece of paper to work out, how to make change for $7.25 using the least number of bills and coins. So with that, you can just say, okay, TAC, but how does that relate to base conversion? I don't see any connections whatsoever. Well, let me present to you, if I were a politician, this is going to be my platform. My platform has nothing to do with what is right and what is wrong. It has to do with changing base 10 to base 2. Okay? Why do we have base 10? Why do we use base 10 numbers to begin with? Exactly. You guys are all sticking your hands and your fingers up, and that's because we got 10 fingers. Okay? There's no other reason to use base 10. It's just not a really useful base to begin with. 10 is not a prime number. It is not the least base that you can use. It is not a power of 2, which makes it somewhat more useful. It's just because we got 10 fingers. If we were born with 12 fingers, we would have used base 12. Okay? So that's really just coincidental and seems to make sense at the time. But it doesn't make sense anymore. Not in this class, not in computer science in general. So we want to do things in base 2. And we're going to start with denomination, okay? How we come up with bills and coins and whatnot. So TAC is proposing, TAC the politician is now proposing that we have a dollar bill, $2 bills, $4 bills, $8 bills, $16 bills, and so on. Okay? So now you don't have to memorize anymore, do you? You just have to remember everything is twice of the one before. So you can work out, well, the next one is 32, and then the next one is 64, the next one up is 128, 256, 512, 1024, 2048, da 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 da. Okay? There's regularity, which is good. Okay? But what about the flip side? The flip side is, okay, divided by 2. So we have half-dollar coins, we have quarter coins, we can even have $8 coins and then $16 coins and so on and so forth. Okay? So that's my proposal. And then you look at this new system and go like, TAC, I would like you to use this new currency system to make change for $7.25. All right, let's do that, okay? $7.25. What is going to, how are you going to figure out, okay, if that is the currency system that we have, how do you figure out what bills and what coins you need to use so that you use the least number of bills and coins to make up for the value of 7.25, which is also known as 7 1/4. It really puts things in perspective because you already know how to do it. It's just that you have been applying your base conversion know-how to a really crooked and weird and convoluted system. Not only is it sort of in base 10, which is not entirely, it is also completely irregular. But this is like super duper regular, right? Somebody told me that you start with the largest denomination. That makes sense, right? So in this case, 7 is, okay, so we'll go ahead and actually do the test here. So I want to see if 7 is greater than or equal to 16. And I'm going to put a question mark here, just so that it's emphasizing whether it's a question. Is 7.25 greater than or equal to 16? The answer is no. So we put a 0 here. False is a 0. All right, so we still have the same amount to deal with. And then the next denomination is 8. The answer is still no. And then the next one is 4. And then the answer is yes. Okay, we got one of those. So now you take 4 out of 7.25, and the remaining portion is 3.25. So now you compare that to 2 and say, yep, it is greater than or equal to. So you have one $2 bill, and the remaining amount is 1.25. But then you move down to $1 bills. Yes, we need one of those, and you took care of the 1. So now we have 0.25 left, and then you ask, do we have half dollar bills? The answer is no. And then down to quarters, and you ask, do we have those? Yes. And even though you can stop at this point, you can always go further because it's just not really helpful, but you can certainly go further. It doesn't hurt anything. It simply says, no, we don't have any one of those anyway, because the remaining amount is now a 0. So a few things to note. One, I don't need division. See, if we are dealing with the normal denomination, when you have $2 and something left, and you have to determine, do we have any $1 bill? It's a division, because you have to divide 2 point something by 1 to figure out that, yeah, we need 2 of those $1 bills. In this case, it's only a comparison. There's no division involved. You're only comparing and subtracting, comparing, subtracting, and so on. There's no division. That makes it easier. Yep.
So how would that like fit in so computers, they use 8 bits now? They use 8
Well,
bits?
I mean, 8, 16, 32, 64.
Okay.
Yeah.
Yeah, so that would fit in yeah, my
Sorry?
bad, sorry, stupid question.
No, it's just that, with 64-bit, you can go all the way to really, really big, denomination if you're talking about money. But it's the same idea. It's really the same idea. It's just which power of 2 do you start with? Do you start with 2 to the power of 64, which is a pretty big number? Or, in this case, do we just start with 2 to the power of 4 because it's an example? That's the only question. So there is a binary number hidden in here. And the binary number, the way we write numbers, is the most significant digit is on the left-hand side. So that's why, if I give you 1, 2, 3 in that order, you interpret that in base 10 as 123 because the 1 is the leftmost and it is the third digit, okay? And which means it is representing the quantity of 2 to the power of 10s, okay? So in this case, the binary number is 0, 0, 1, 1, 1, 0.101 in base 2. The reason why there's a point or a binary point, we don't call it a decimal point anymore because we're working with binary. So the binary point, or even the decimal point, is really just a separator so that we know where the quantity of 1 is and where do we start the quantity of the fractions. We need a little indicator because otherwise it's just a whole bunch of digits. We don't know where the fraction is supposed to start. So the point is really just a notation to say, hey, everything to the left-hand side correspond to quantities of 2 to the power of non-negative powers. So that would be 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, blah, 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 like that. And then everything, all the digits to the right-hand side of the point represent quantities of 2 to the power of negative powers of 2. So this is telling us how many 2 to the power of negative ones, how many 2 to the power of negative 2, how many 2 to the power of negative 3, and so on. Is that interpretation unique to binary numbers? No. We do that with base 10 numbers without thinking about it. I'm just bringing out something that you know already. It's just that most people do not crystallize the concepts the way that I do in this class. Are we still doing okay so far with base conversion? We are good? All right. So base 2 is useful because inside the computer, everything is a 0 or 1. And that has to do with how we interpret voltages. Because inside the computer, we say, well, if the voltage at the gate is below a certain point, we will interpret that as a 0. If it is above a certain point, we interpret that as a 1. So that is why computers are quote-unquote binary, because of the way we assign values to the physical quantities. But when we are talking about base conversion, there is no need to stick with just base 2 or base 10. We can certainly work with base 7 as well. Yeah, I can see how people can cringe when we say base 7. Ugh, who would use base 7? I will explain that in just a little bit. I can think of 2 examples where base 7 is useful. Okay, so let's take a look at what we know as 2000 in base 10 and try to express this as a base 7 number. And we'll try to figure out the digits of the base 7 number. In fact, I am going to name the digits so that it's easier to talk about which digit we are talking about. So we'll try to figure out, these are just placeholders. A is a placeholder for a digit, B is a placeholder for a digit, and C is also a placeholder of a digit. So in this case, C is the quantity of 7 to the power of zeros, otherwise known as 1. That's how you read a number, okay? The least significant digit to the left-hand side of a decimal point, in this case we don't have any points, is representing how many ones we have, okay? B is representing the quantity of 7 to the power of 1, which we know as just 7. And then C is the, A, sorry. And then A is the quantity of 7 to the power of 2, which we know as 49. And I think we need one more, so we need okay, what should I use as a symbol? Because I need one more digit.
Z.
Z, okay, fine. Z is the quantity of 7 to the power of 3, which is, okay, so this is, I'm testing how quickly you can do mental math, or do you know the tricks? So it's 343, okay, without using a calculator, because it is 49 times 7, so you round 49 up to 50. 50 is an easy number to multiply by 7, 350. But since I'm missing 1, so now you use algebra to subtract 7 from 350, and you get 343. All right, so I think that should be sufficient. There we go. So are we doing okay so far with what each digit is trying to say when we express a value as a number, in this case in base 7? So what base we choose to use is only changing the base of the exponent. That's it. That's all. Okay? The quote-unquote normal number that we are used to, we use 10 as a base. And then the binary numbers, which are super duper useful in computer science, is using 2 as a base. I just choose to use some really odd number. Not only is it odd, it is also prime for the base, just for the heck of it. But there's no problem of using 7 or 11 or some other value as the base, because hey, it's just a base. All right, so now you already know that we should start with the most significant digit. So this time we are going to start with Z, which is basically asking how many 343s can we fit in 2000.
I mean,
No.
Aren't we supposed to go like 7 to the 4th? Because
No,
no.
because this is all we need. Because if you multiply this by 7, it's already exceeding 2000, right? So we know we have enough digits to begin with.
We can fit 5.
We can fit 5. Sounds about right.
Yeah, I did that.
Okay. All right. So now we say, what is 2000? This is in base 10 divided by 343. The answer is the quotient is 5 with a remainder of. Okay, let's see if we can do mental math really quick. So 5 times 343 is, okay, my mental math sucks. So I'm gonna cheat and use an actual calculator. $2,000 divided by 343 is 5. Okay, I need to find the remainder. So it's 2,000 minus 323 times 5, 285. Is that right?
Yeah, that's nice.
Okay. So now we switch back to, oh, okay, I don't need to switch back. It's a different tab. Okay, where is that one? Where's the one that I'm supposed to be on? There we go. 285. There we go. All right, so now we know, we only have to handle 285 at this point. So now the next question is, what is 285 divided by the next power of 7 down, which is 49? Well, that one is easier, right? We know 6 is going to be too much. It's going to be another 5. And the remainder is, so if it's 5, it is 245, 245. So we have a remainder of 40, I think. Well, let's double check. See, I can use a really simple calculator that is incapable of doing mod, and just, it's just a little bit more work. 49 times 5, and the answer is in fact 40. So I just want to double check. So now we look at 40 and ask, okay, how many of 7s, can we fit into 40? And that turns out to be 5 too. That was coincidental, okay? I did not intend to make this happen, but it just so happened to be like this, and the remainder is also 5. And then we do the next one, which is 5 divided by 1 is 5 with a remainder of 0. Okay? Now you can say, we can stop here. But you can also say, but Tech, if I want to continue to go and keep dividing, is that okay? The answer is, yeah, absolutely. Because now we can say, what about 0 divided by the next power of 7 down? But wait, Tech, we just worked with 7 to the power of 0. What other powers of 7 are we talking about? Come on. You guys have seen it already earlier in base 2. -1. 7 to the power of -1, which is just 7th, right? 1/7. So now we can say, okay, fine, this is just the value we're going to divide it by. And the answer is obviously 0, because if the dividend is a 0, it doesn't matter what your divisor is. It's going to be, the quotient is going to be 0. And if you want to keep going, that's fine, but I'm just going to stop here. So that means, 2,000, what we know as 2,000 in base 10 is 555.00000 in base 7. It works out. I just did not know that 2,000 is all 50 in base 7. It just turns out that way. With 5 minutes remaining, I'm going to explain why base 7 can be important. First of all, if octopi, the plural form of octopus, are intelligent and they need to represent numbers, they're going to use, and I know what you guys are saying, but tag octo means 8, Yes, I know that. And 7 is 1 less than 8. But they need one tentacle to hold on to the beer as they do counting. I mean, how many times did it bother you that, once you use one hand or 5 fingers to hold a beer, you can only count up to 5? That sucks. So change the base, right? Change the base so that you always have one tentacle left to hold onto the beer. And if, for those of you who say, but that doesn't make sense, how do you drink beer underwater? I recommend you to watch SpongeBob.
They use the one tentacle to hold the calculator to convert to base 10.
Octopus, yeah. In the entire show of SpongeBob, my favorite character is Patrick. I think he's the wisest of all the characters. It's just that people do not, understand that part. It's just like Mr. Pang in Kung Fu Panda is probably the wisest, character in the entire movie. It's just that, people do not recognize him as the wisest, character. People think Wu Gui, is the wisest. But remember, every single event, key event, Mr. Pang is a key component to every single important twist in the storyline. How did they get to the temple? How did they get into the tournament or watch the tournament? Mr. Pan said, oh, they're going to have a lot of people. We got to sell noodles. And there we go. Anyway, and then the other one has to do with the movie Arrival. Have you guys watched Arrival, the science fiction? And if you have watched it, what is special about the aliens, other than they're kind of huge and they use circles with special marking for communication?
Do they happen to have different number of fingers?
They have 7 limbs. They're haptopods, pods.
Oh,
Yep.
I didn't know. I just said it's a common theme in sci-fi where they have different fingers.
Mm-hmm.
These different types of fingers.
Yeah, but in this case they chose the number of limbs to be not even an even number. I mean, if you watch Star Trek, all the aliens are humanoids. It's like they got 2 eyes, 2 hands, two legs, and so on. It's like, yeah, what are the chances that is the case, right?
They all happen to speak English.
Well, they have the universal translator to kind of get around that problem. So anyway, are there any questions about Bayes conversion? It is not, yeah, go ahead.
Are we doing negative numbers?
But negative numbers are just you're putting a sign in ahead of the number until we get to unsigned number representation, which is further down. So,
Floating point.
a floating point is easy. Once you understand this stuff here, floating point is just saying, okay, we got this we got this 1 point blah 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 number here. The question is, what is the unit, right? Is the unit 1? Is the unit 2, 4, 6, 2, 4, 8, 16, and so on? Or is the unit half, quarter, eighth, and so on? So from that perspective, once you understand this representation, floating point numbers is like, there's nothing special about it. We'll get to that point. Okay, so let me, before we get on to the lab, let me remind you guys what you need to do over the weekend, because I have just basically talked about everything in this particular module, but without resorting to math whatsoever. So you need to read this particular module and basically understand the math, how we work out the math, because there are actual equations here that can help you do the Bayes conversion. And if you want to ask me, but what is B and what is D and what is B? You have to read the module to understand that part. So use the weekend to read this entire module, but the main concept is done already, okay? I have already explained how to do Bayes conversion by hand. So the rest of what you need to do is really just kind of read through the module and get all the details down. Remember, for each hour in lecture, you're supposed to spend 2 hours outside of the lecture. And I think it will comfortably cover this entire module, because we have a 80-minute lecture, which means 160 minutes outside of lecture sometime before next Tuesday to kind of review this material. And take notes along the way as well, because taking notes when you're reading is also helpful. If you remember, I sent you this document of how to understand something, and I gave myself the task of trying to understand quantum computing. This is basically my notes. Okay, if you ignore all the discussion of your understanding and all the boxes on the right-hand side, the rest, all the technical stuff, that is my notes. Okay, I look at these symbols and go like, I have no idea what that is. So I look it up. I look up the definition of a symbol, and it has even more symbols that I don't know. What do? Look them up. And then just recursively, quote unquote, recursively do that until I get to the point where I go like, yeah, I think I got that. And then have to backtrack to go back to what I was trying to understand to begin with, move on to the next thing that I do not know, and do the same thing over and over and over again. So that means, if you want to understand content in a deeper way, I don't think it has to do with IQ. I don't think it really has to do with intelligence. It really just has to do with keep working on it and keep track of what you have discovered so far. It really has to do with that. And also, I got 1-star quality that I find that most people do not have, is I know when I don't understand something. I can look at something, it will talk about something, and I go like, no, wait, I really don't understand what that means. That is my one single superpower. that I thought, from observation that many people do not have. But other than that, it's really just keeping at it, which means you have to allocate enough time, okay? Because you cannot just say, I'm going to do what Tech said, 160 minutes. I'll allocate 20 minutes. I think I'll be fine. No, that is not probably fine. So you have to give yourself enough time to basically just kind of keep drilling down until you get the fundamental of the concepts. All right. So I'm going to give you guys a 10-minute break, and then at 10:30, we're going to start the lab. I will give you the solution to the previous lab so you can use my solution as a starting point, just in case you don't feel comfortable using your own. And then the lab will end at 11:50 a.m. Okay, so check your phone. It's a test. Yeah. This is only a test, okay? So we are not evacuating the building. The lab is on. I'll see you guys at 10:30. Go ahead and take a break if you want to. Go get something to eat or just rest, drink something, and I'll get everything ready by 10:30.